So today we will be learning pipelining. As the name suggests, it is a technique to decompose sequential process into certain sub operations. Like we are given one process and we will divide it into certain sub parts, and we will perform the common parts in parallel manner. For example, we have taken this here. The multiplication has higher priority, that's why we will perform it earlier, and then addition has slightly lower priority, and we will repeat it for 5 times. There are 5 iterations, 1 to 5. So firstly, we will divide it into 3 segments. The first segment consists of R1 and R2. These are 2 registers. We'll load AI and BI. I will be 1 and 1 for the first case, for the first iteration. This is segment 1, this is segment 2, and this is segment 3. Now the data from R1 and R2 are taken as input for this multiplier, and it performs the operation, and the final output is stored in R3 register 3, and the CI, which is the third operand, is taken and stored in R4 register 4. Now in the third segment, adder takes the input from R3 and R4 and performs the operation and stores it in R5. In similar fashion, when this 1 is done, we'll perform 2, 3, 4, likewise 5. Now here we will get to know why this is named as pipeline. Like, as we have learned that we will be putting the input data A1 and B1 in register R1 and R2. Now in the second segment, this will be multiplied and stored in R3, and in the second segment as well, we will be taking the data for C1. Now in the third segment, this multiplied part, and we'll add C1 with this. Now finally we are getting the final answer at this stage. So it has taken 3 clock pulses or 3 cycle time to reach to this final data. So when we are considering a pipe, if this is a pipe and we start pouring water from this side, so we know that we'll get water from this portion after a certain amount of time. For example, at one cycle time it reached here, in the second cycle time it reached here, and after third cycle is over, we'll get to see the water on the other side. In a similar manner, even when we stop pouring water from this side, water will still remain inside it, and once it is completely emptied from this portion, then only water will stop pouring out from this. Now, as we have read earlier, that this will be performed in contiguous manner. So when this in segment 2 this multiplication is happening and C1 is being loaded on R4, at the same time we will be loading A2 and B2 in register 1 and 2 respectively, and in a similar way we'll then pass on it to the next segment where the multiplication of A2 and B2 happen, and C2 is being loaded on R4, and in segment 3 again this final operation is being done and we get the final answer. So this is the thing which we can see, that this segment 1, assume it as person 1, and this is person 2, and this is person 3. So here when the person 1 first finishes the task, at that time P2 and P3, they are sitting idle, they are doing nothing. Now when the person 2 is performing this operation which is being passed on from the person 1, at that time the person 1 will take up the next iteration, which is 2. A2 and B2 is being stored in R1 and R2. In a similar way, when segment 2 or the person 2 has completed his task, he will pass on to this person 3, he will do his job. At that time the segment 2 will not sit idle, it will take on the data from segment 1 and they will perform the task. So in this manner we are able to save some time, and this is how pipelining helps us. Now from this chart we will get to know how much efficient this pipeline is. So here we have taken 5 iterations or 5 tasks are being assigned. Now for these 5 tasks to be performed, we have taken 1 to 7 cycles. Total 7 cycles are being taken. If it was on non-pipeline system, in that case we have to wait for the output from the first segment once he has done all the tasks. For example, he is doing this task and then simultaneously passing on this to segment 2. But in non-pipeline case, he will perform all these 5 tasks, then only from here A1 into B1 and C1 this thing will happen. This similar thing will happen with segment 2. This person 2 will perform all these tasks up to A5 into B5, and C5 will be loaded. Then afterwards from here this segment 3 will start performing the task. So they individually take up 5 clock cycles, and since there are 3 segments, it will take 15 cycles. There is no merging, or as we can see that there is no parallel function that is going on. Each of them are independent of each other, there is no such dependency. However, in pipeline case we can see that they are performing simultaneously and saving some cycles. So How this is helpful? This pipeline processing can be helpful when we have a high amount of tasks, when the number of tasks is on the higher side. Like when we have 5 tasks, we needed 7 cycles. When we have 6 tasks, we have 8 cycles as compared to the 18. A similar way, for 7, we need 9 cycles for pipeline and 21 for non-pipeline. Now another important aspect is pipeline cycle time. Now what this means, it means the minimum time in which all segments perform the respective sub operations. So when we were given n equals 5, means 5 tasks were given for pipeline, we were taking 7 cycles. And on the other hand, when we are given with non pipeline, it will be taking 15 cycles, because there is no parallel functioning or there is no overlap. And in order to find the total execution time, we'll multiply the total number of cycles with the cycle time. Now we'll use a few notions. Now we'll look into two cases. One is pipeline and one is non-pipeline. That we'll denote the segment with K, and the cycle time for pipeline will be TP, and for non-pipeline it will be TN, and the number of tasks, it will be denoted by N. So in order to perform one task, it will take the number of segment into the cycle time, and for the rest of this task, means n tasks are given, first task is performed, and for the remaining task n minus 1, we will multiply it by TP, and the total time will add up these two things, we'll get K plus n minus 1 into TP. This is a crucial formula for pipeline. Now for non-pipeline, a similar thing will be done, but we'll use n into Tn. So for the previous example which we have seen, we know that we were given 3 segments, the number of tasks was 5, and assume that TP is something which is not given, but assume it to be 2 nanoseconds. So here the total time required in case of pipeline will be K plus n, 3 plus 5 minus 1 into 2. This is an assumption, 2 is an assumption, it will be given in question. So this comes out to be 7 into 2, which is 14 nanoseconds. In a similar way, in non-pipeline we know that there are no segments present, so K will be of no use, but Tn will be given in the question. Let's assume Tn to be 3 nanoseconds. Number of tasks is 5 and Tn is 3, so it will be 15 nanoseconds. Now another important topic related to this pipeline is speed up ratio. Now what this means, it is a ratio used to measure the performance of the pipeline or the efficiency of the pipeline. We'll use this trick, slower technique divided by faster technique, to get the performance ratio of this pipeline. So we'll divide it on numerator, we'll put non-pipeline time, in denominator we will divide it by pipeline time. So this was the formula which we have studied earlier. Divided, we will be getting speed up ratio. This speed up ratio is denoted by S, and this speed up ratio also has a modification. When we are asked for ideal speed up or either this maximum speed up, we'll assume that K minus 1 is very less than n, so it becomes negligible, or we'll put a 0. So this becomes, the same formula becomes n into Tn divided by n into Tp. N gets cancelled up, we'll end up getting this formula Tn by Tp. Now when it is given in the question that in order to perform one task the time is equal, then this Tn equals K into Tp. So finally we will get this speed up is directly equals to K. Now this is a special kind of pipeline which is synchronous pipeline. What makes it synchronous is this buffer register which is set up after each segment. Means once this segment is taking 8 nanoseconds, it will reach this buffer, it will take 1 nanosecond, this will adjust and synchronize the whole process. In a similar fashion it reaches here after passing through this buffer register. In case of pipeline, we use these buffers, and in order to find the cycle time, the clock cycle time, we'll find out the maximum of all these segment delays. Like segment 1 is having a delay of 8 nanoseconds, and segment 2 is having a delay of 9 nanoseconds, 7, 6 and 1. So out of these we'll take the maximum one. So here 9 is the max, and along with that, we will be adding the register delay. Here the register delay is of 1 nanoseconds. So finally the answer will be 10 nanoseconds. Now for the non-pipeline system, we will add up all the segment delays, because we have seen that they are not working in parallel fashion. So they will add up all the segment delays, and in this case we will not be considering these register delays or buffer delays. So the answer will be 30 nanoseconds.